Right, okay, so sorry about the problem with the fire alarm. Hopefully we'll carry on. So I was talking about the lab sheets. So these are purely to give you practice for your coursework. Okay, teaching schedule. So there are 12 weeks in the first term, and so this this table on page B, okay, basically says teaching schedule. These dates are slightly right.
You're right.
Yeah, that should be 26. Okay, hopefully it's better. Remember, this is an old form of the slides, but this is a rough sort of teacher schedule. So today's just going to be introduction and some definitions, nothing too tricky. Next week we'll start on what we call finite difference approximations, etc. So that table will let you know what we're doing at particular dates. And also on that table is when you may see something called, for example, Lab Sheet 2 submission, and then the week after, Lab Sheet 2 peer review. So essentially, you should submit your lab sheet work by, for example, week 4, and then the following week, you should do the peer review. And I'll explain more about that if I've got time at the end of this session. Right, so I'm now going to start sort of introducing you the idea of partial differential equation. So this is on page 1. Okay, you have, quite a few of you also do the ODEs unit, which is ordinary differential equations. Now, ordinary differential equations are equations which are written in terms of a variable, independent variable, normally t or x, and it can only have one of those variables. Okay, partial differential equations can have multiple independent variables. Okay, so the official definition is a PDE is a differential equation expressed using a function of 2 or more variables and the partial derivatives of that function. So the function here in question is u. So big U is our function. Okay, that U tends to be the standard in the field or in the discipline to actually represent that function. You're familiar with the partial derivatives. So when we say a partial derivative of something, we're talking about the change only in terms of with respect to that variable. So for example, partial derivative of u with respect to x means what's the change of that function u just in terms of x. Okay, it's different from an ordinary derivative. The partial derivative is only with respect to that variable. This becomes a bit of a sort of a handful to write out these all the time. So we use a shorthand notation where the subscript denotes the partial derivative. So for example, big U x with the subscript, that's shorthand for saying the partial derivative of u with respect to x. If we got the second order derivative, so here we have a second order partial derivative, we simply write it as u x x. If we've got a mixed derivative, because you can have mixed partial derivatives, okay, the subscript just gives you the variable that derivative is with respect to. I tend to use this form most of the time, but can be sort of interchangeable. Okay, so that's what a partial differential equation is. Okay, PDEs are very, very useful. Okay, they allow us to do lots of nifty things. So, for example, weather forecasting is one of the main ones. Aerodynamics, fluid flow modelling, combustion problems. These are all problems that can't really be solved using ordinary differential equations. So PDEs have far more sort of relevant to application to the real world than ordinary differential equations. Quite a bit of this lecture is going to be about terminology and about definitions. So we'll start with the order. The order of a PDE is the order of its highest derivative. So if we have this one here, you can see we've got a first order derivative because there's only one x there. Okay, so that's the function u, first order derivative with respect to x. and here we've got the function u, first order derivative with respect to y. So that's known as a first order partial differential equation. Here, essentially, I just did a copy and paste and stuck another x on the bottom there. So this now becomes a second order derivative. So that's what we refer to as second order PDE. Now, unfortunately, in mathematics, we also use the word order to mean an order of accuracy. Okay, so we use it in two different senses. We use it in the sense of, okay, what's the order of the derivative? And we also say, what's the order of accuracy? It's annoying. I don't know why we use the same word, but we do. So it's very context sensitive. So beware not to sort of confuse the two. And a PDE is a linear PDE if it can be expressed as a linear combination of the partial derivatives. Okay, so you have nonlinear and linear PDEs. Okay, a few more definitions. These are quite important. Okay, the domain of a PDE is all of those values of the independent variables for which the PDE exists. Usually, with PDE, we think of domain as being time, which is normally represented by t, and space, which is normally represented by x. Or if you've got 2D space, you've got x and y. Or if you've got 3D space, you've got x, y, z. Okay, so the domain is a set of all values for which that exists. So, for example, if you're modelling flow within a tank, so let's say you've got a water tank, and you're modelling the water flow within that tank, your spatial domain would just be the space within the tank. Okay, so nothing outside the tank is of any use to you, so that's not in our domain. Okay. Initial conditions. So these are the values or conditions placed upon U, which are defined for the initial time scale. Okay. So normally we start, if we're modeling something, we start at t equals 0. So time is equal to 0 seconds. Whatever your condition of the system is at that point is what's known as the initial conditions. So let's say let's talk about my water tank example. You may be modeling a water tank, and to start with, the water is still. So it's sort of the velocity of the water will be 0 everywhere. There are what we refer to as initial conditions. Boundary conditions. So these are conditions which are placed on the edge of the domain. So you'll have a boundary domain. The domain doesn't go forever. It must have a boundary somewhere. Now, sometimes at that boundary, we want to place a condition on it. So, for example, again, my water tank example, the boundary of the domain would be the boundary of the water tank. And one condition we may want to place is that no water can pass through the sides of the water tank. So that would be one such boundary condition. Okay. So initial conditions, what does the system look like? To start with, boundary conditions, what happens at the boundaries of the domain. And finally, perhaps, well, I suppose the most important is the solution. Now, the solution of a PDE, what we're trying to do is we're trying to find the values of this function u. Okay, so all of our PDEs are expressed in terms of partial derivatives on u. And what we're trying to do is find out what that function is. Now, for the vast majority of cases, 99% of cases, there's no exact solution. Okay, with differential equations, it's very rare that there's an exact analytical solution. Okay, hence why we need to use numerical methods. Okay, so this is what we're trying to find. We're trying to find an approximation of u. Okay? And that solution has got to satisfy the PDE. So if we find some values of u, it has to satisfy the PDE. No good if it doesn't, because we're not solving that equation. And it also has to satisfy the initial conditions and also the boundary conditions. Okay, so on page 3, can we do some a worked example now? I'm going to try and actually get this to work through the, yeah. Okay, don't know whether this will work or not, just placing it on the camera. No, doesn't have to. That's a good question. There's a question here about the equation right at the bottom of page 1. It's a linear PDE. You can see here derivative in terms of x, derivative in terms of y. You don't have to have the derivative. It's just that function u. Okay, so there doesn't. That's not a typo. There doesn't have to be any derivative there. I'm just going to move this slightly forward so you can see. Right. So I mentioned there's this worked example. Okay, so I've got this PDE, and this just so happens to be what we call the heat diffusion PDE. So if you're doing a project on heat diffusion, perhaps that'll be important to you. Okay, and what I'm saying is, given these initial and boundary conditions, this is the solution. So this PDE happens to have an analytical solution. Okay, so this u is a function of the independent variables t and x. T is time, x is space. So when t is equal to 0, I'm saying the initial conditions correspond to 2 times sine pi x over L. So if you imagine a one-dimensional bar, like a metal bar, okay, of length L, what we're doing is we're saying if the initial temperature across that bar is described by this function, then that's a solution for time t and space x. So that first equation there is the initial condition. These two are the boundary conditions. So this is the value when x is 0. So when x is 0, we have the temperature of 0. And when x is L, so that's at the other end of the bar, temperature is also 0. Okay, so that's initial condition. Those two are boundary conditions. And the example says, okay, show that it has that solution. Okay, so in order for that to be the solution, it has to satisfy the PDE to start with, also has to satisfy the initial conditions, also has to satisfy boundary conditions. Okay, so there's our PDE. And on the left-hand side, we have u, which is this function, differentiated with respect to t. So what I'm going to do here is differentiate this with respect to t. Remember, it's partial differentiation. If we look at the first part, the 2 sine pi x over L, there are no t's in there whatsoever. Okay, so that's a constant. So if I'm only looking at the partial derivative in terms of t, this is a constant. So that's going to just stay as it is. Here we've got the exponential function of some function within that, and that's got a t in there. So simple application of the chain rule. Okay, so the derivative is going to be of this is going to be minus 2 k pi squared over L squared. Okay, so that's the derivative of that function in there, because it's t, obviously t just disappears, and that's multiplied by that 2 there, by the way. Okay. And that's going to be multiplied by sine pi x over L, and that's multiplied by the exponential function. Well, one thing which last year's student moaned about me is the fact I'm left-handed. So you may notice when I'm working on the visualizer, I do this a lot. Sorry about that. Nothing I can do, unless you want me to write with my right hand, and I don't recommend that. So. Okay. Everyone see where that comes from? Straightforward partial derivative of that. So that means my left-hand side of that equation is done. Now I need to calculate the right-hand side. Okay. To do so, I need to differentiate u with respect to x. I need to do that, actually I need to do it twice because I need the second order derivative. Okay, well in this case, this is a function of x, that's just a constant, there's no x's in it. Okay, so if I find the derivative of this, we'll have 2 pi over L pi x over L multiplied by that exponential. And because that doesn't have any x's in it, that's just a constant. Okay. Hopefully you can all see that. I haven't done anything apart from differentiate. Obviously I'm going to do that again because I need uxx. So all I do is just differentiate this again. What's the derivative of sine?
Cosine.
Not quite. Minus cosine. Okay, sine goes to cosine, cosine goes to minus sine. Oh, sorry. Nobody spotted that error. You differentiate sine, you go to cosine. That wasn't deliberate, that was me being a bit silly. Sorry. Yeah, so what's the derivative of cosine is minus sine. Sorry about that, you were right, whoever said sine was to cosine. Yeah. Okay, so if we differentiate this, we end up with minus 2 pi squared over L squared. Okay, because 2 pi over L times pi over L is 2 pi squared over L squared times sine of whatever was in the bracket times the exponential. Okay, so now I've got my second order derivative. Okay, so if I put it together, so my equation was ut equals k uxx. So ut on the left-hand side is this. Oops, sorry, it's that. So minus 2k pi squared over L squared sine pi x over L e minus kx squared t over L squared. So that's a bit on the left-hand side. On the right-hand side, I've got k times all of that. So I've got minus 2 pi squared k over L squared. Okay, so I'm multiplying that by k times sine pi x over L e to minus k pi squared t over L squared. What can you tell me about the left and right hand side of that equation? The same. So that shows that this function up here satisfies our equation. Okay, so we know that ut is equal to k uxx. That's a big tick there. Okay, so we satisfied the equation. But that's not enough. We also have to check initial conditions and boundary conditions. Okay, well, if this is our solution, the initial conditions is that when t is equal to 0.
You know, on the second derivation.
This one.
Yeah, that one. How can you gone do pi squared?
Because if we use the chain rule on cosine, so let's say u is the contents of that bracket.
Oh yeah.
So if we differentiate the contents of the bracket, and then we differentiate the function.
Oh, okay.
Yeah. So that derivative of that would be pi over L. Then that goes times that pi over L. Derivative of cosine is minus sine. Okay, what I'm going to do now is for the initial conditions, I'm going to evaluate this when t is equal to 0. So in this case, we've got 2 times sine pi x over L times the e. Well, if t is 0, all of that is just going to go to 0. You see that? Just all goes to 0. What's e to the 0? What was? Okay, so we have 2 sine pi x over L, which just so happens was what we said was the initial condition. So this is what we think is a solution evaluated at t equals 0. So that's the initial condition satisfied. IC means initial condition or shorthand. Last thing we need to do is the boundary conditions. And we do the same, but this time at the two boundaries. So we do the same. Okay, that's ut when x is equal to 0. So what I'm doing is I'm looking at this function, but instead of t being 0, I'm now looking at x equals 0. Okay, so we'll have 2 times sine of 0 times e to the minus k pi squared t over L squared. What's the sine of 0? 0? Yeah. Okay, so that's all just going to collapse into be 0. Okay, so that's the one boundary done. Got to look at the other boundary now. So the other boundary is when x equals L. So it's right at the other end of the sort of bar. Okay, so if I set L into x here, okay, I'm going to have pi L over pi times L over L, which is just going to be pi. What's sine of pi? The other one, yeah, 0. So that's all going to be 0. Okay, so up here, I said my two boundary conditions are always going to be 0. If this is the solution, I test it for both boundaries. They're both 0. So everything, so that's, we know that's a solution.
You're on the third round, right? Did you put the same thing chance?
Which one?
Follow up. Just a bit of, yeah, that one.
Basically, what I was doing there was that is ut, that's kuxx. Okay, so that is ut there. So I put that on the left-hand side. Then I have uxx multiplied by k on the right. So I'm testing them both equal to each other.
Would kuxx be minus 2 times square root of L?
It would be if I didn't have that there. Sorry about that. Always got to check. Always got to check my working.
I think you said
Did I say it squared, but I didn't write it down? My apologies. Okay, so that's basically this example shows that that function there is the solution to that PDE. It satisfies the PDE, which we showed here. It satisfies the initial conditions, and it also satisfies the boundary conditions. This is very unusual, very, very unusual to have an exact solution to a PDE. Why should it just be me who gets filmed? Oh, I hate it when it does that. Hang on a sec, I just got to. Technology is not quite there at the moment, I don't think. Got to try and do it. Do it by looking at that one there. Okay, so we looked at the solutions, initial conditions, and boundary conditions. Okay, classifying PDEs. There are 3 main types of PDEs. Okay, and we classify them as this. Okay, so if we have this PDE of this form, so you notice it's a second order PDE, and it's got all the different possible up to second order PDEs that we can have. So double x derivative, mixed derivative, double y derivative, first order in x, first order in y. Now we classify PDEs as one of these 3. You can either have an elliptic PDE, parabolic, or a hyperbolic. Okay, and different types of PDEs require sort of different solution methods. Not too different, but there are subtle differences. And they're satisfied using b squared, which is the coefficient of the mixed derivative, minus 4 times the coefficient of the second x derivative times the coefficient of the second y derivative. B squared minus 4ac is fairly familiar from work with polynomials, second order polynomials. These names are based upon what we call conic sections. If you take a cone and take a slice for a cone, you have one of 3 shapes. You have an ellipse, you have a parabola, or you have a hyperbola. Okay. The reason why the names are based upon that is by pure fluke. Okay. It's nothing to do with conic sections. So we just take the name from there. So I don't think there's some form of tie-in with it. It's not. Okay. Elliptic PDEs. Okay, these are used to model steady state problems. So this is where the solution never changes over time. So there's no t variable in our PDE. Okay, so for example, electrical fields, magnetic fields. If you've got a magnet, around the magnet there are, well, what we call a field. There'll be a positive and a negative. Okay, that doesn't change over time. It may do if we input some external force, but some external influence on it. But generally speaking, it doesn't change over time. And that's an example of an elliptic PDE. Okay, initial conditions do not affect the solution. So you can have any initial conditions you want, and if you solve it, you'll get the same solution. So that does have no effect. Boundary conditions do. Okay. Solutions are smooth. So generally speaking, solutions to PDEs are smooth. Sometimes we don't want them to be, but generally speaking, they are. And examples are, a famous example is what we call Laplace's equation, which is quite simply double derivative in terms of x plus double derivative in terms of y equals 0. Then Poisson came along, stuck a function on the end of Laplace's equation, called it Poisson's equation. Very, very similar, but we just have a function on the right-hand side. We'll be looking at solving those in about 3 weeks' time. They're quite easy to solve. Okay, there's an example of a solution. I just nicked that off Google. It's not plagiarism if you admit to it. Okay, parabolic. Okay, these are PDEs that model diffusion. Okay, so for example, heat diffusion. So if you have like a metal bar, you have it temperature across the bar can be modeled by the heat diffusion equation. In parabolic PDEs, solutions do change over time. So therefore, they're affected by their initial conditions. So if you start off with different initial conditions, you'll have a different solution. Initial conditions and boundary conditions influence the solution. And here we have the example of the heat diffusion equation. Okay, I think so. This alpha is some conductivity parameter. So depending on if you've got metal, that's a very good conductor of heat. That might be a certain value. If you've got wood, very poor conductor of heat, so that might have a different value. And we'll be looking at solving that later this term. Okay, they were meant to be more. There we go. Don't know what happened there. Here's an example, and we'll have a look at this. This is, imagine you've got a square metal plate, and you get a brand in the shape of the C. You run that brand in a fire, it heats up, and then you stamp the plate with that brand. So there's a C-shaped hot region, and all the rest of it is, excuse me, I'll just turn off the notifications. C-shaped hot region, and all the rest of it is cold. And after a while, what happens is the hot region heats up the bit around it, and it all sort of smudges out, which is a technical term. Final one is perhaps the most important and most sort of exciting ones, hyperbolic PDEs. These model propagation, anything moving from one place to another. Okay, the hyperbolic. So for example, weather. weather systems move around. You have different pressures. You have, well, we just had rain. Now we've got sun. Okay, so things moving. Aerodynamics is another example of hyperbolic PDEs. Okay, so the solution does change over time. Solutions are affected by the initial conditions. Example, very, very simple one, is what we call the advection equation. We'll be looking at methods to solve that. The advection equation does have a analytical solution. And there's an example. So that's what we call a dam break. So we got hyperbolic PDE, they're modeling water. And what you have is you have two bodies of water, an upstream body separated by a downstream body, which is got a partition or a dam in the way. If we remove a portion of that dam, the water is allowed to flow out. And that's an example of a hyperbolic PDE. And we'll be looking at solving that. Probably last couple of weeks of term, we'll be looking at solving water flow problems. Okay, more terminology. Don't worry if you can't remember all this terminology. What I would like you to do after this session is just have another read through of chapter 1. We're going to talk about domain of dependence and range of influence. Kind of rather grand names, I think. Kind of almost, I don't know, science fiction-ish. But the domain of dependence is a set of all points in the domain that have an influence on the value of the solution at this point. Okay, so if a change in the value at another point affects that point, then the domain of which was the bit we were changing is in the domain of dependence. The range of influence is kind of like the other way of looking at it. It's a set of all points for which, if this point changes, what points does this affect other points? Okay, bear with me. I'll give a couple of examples of that. Okay, elliptic PDEs is easy. Okay, for elliptic PDEs, the range of influence and the domain of dependence is the same. Okay, you basically take the domain, which here we've got a 2D domain. We've got X direction and we've got the Y direction. And let's say this is our domain, this rectangular region here. All points have an effect on all other points. Okay, so if I was to change the value of a point down there, that has an effect on the value of a point up there. Okay. Likewise, vice versa. If I change this point, this will then affect that point down there and all other points in the domain. Okay, parabolic PDEs. Now, the main difference with parabolic PDEs is they change over time. So in this case, I've chosen an X domain, which is space, on the horizontal, and this vertical one is time. Okay, so if you imagine that on this bottom line, this is like your initial conditions, and as you go up, you're sort of going forward through time, and you're changing the conditions. So let's say, so what this means is any point on this dotted line is affected by any point in the pink region. So any point in the pink region affects the point on the dotted line. And looking at it the other way, if we look into the future, which is the blue bit, which is forward in time, all of these points on the dotted line affect all of these points forward in time. Okay, so think of domain of dependence as being like backwards in time and the range of influence being forward. Okay, the trickiest one perhaps to understand is the hyperbolic PDEs. Okay. Remember I said hyperbolic PDEs are all about things moving. Well, I wanted to do a little thought experiment now. Think of a swimming pool which is completely at rest. Okay, so swimming pool completely at rest, and you just got changed, you're into your swimming costume. What's the first thing you do when you get to the swimming pool? You do a bomb, don't you? It's completely at rest. It's too inviting to do a bomb. So you go to the deep end, you run and jump, and you do a bomb. somebody down the shallow end, the other end of the pool, is not going to feel the effect of your bomb until those ripples, those waves get to them. Okay, maybe 5 seconds, 10 seconds afterwards. Okay, that's what we have here. Okay, let's say you did a bomb and this is you here. Somebody elsewhere at the other end of the pool is not going to feel the effect of your bomb, no matter how magnificent it was. Okay. So as we go forward in time, so let's say the bomb was there and somebody out here not going to feel the effect. Okay. What if that was the bomb? Okay. Somebody here won't feel the effect until we get forward in time. And then, so somebody here, as it goes forward in time, that's when they start to affect it. Somebody close to you will be affected a lot quicker. Somebody further away will be affected a lot later. Okay, so you'll see these sort of cones, sort of range of influence, domain of dependence. That's for propagation problems. That's for anything that models movement. Okay. The boundaries of these are the fastest possible speed permissible by that system. So, for example, if you're dealing with water, this boundary is normally the speed of sound. Because nothing, you can't, water can't jump fast. Generally speaking, can't jump faster than the speed of sound. Sound's a good one. Acoustics. If you can't possibly have any sound traveling faster than Mach 1. Okay, so these lines will be the speed of sound as well. Right, so there were a lot of terminology there. Initial conditions, boundary conditions, solution, elliptic, parabolic, hyperbolic equations, etc., etc. I'm not expecting you to fully grasp all of them straight away. So what I do ask you to do is just have a read of that chapter afterwards and try and sort of learn them. Okay, what I'm going to finish off with is an idea of how we actually approach this problem solving with, with any sort of form of numerical method. Okay, and this is a general methodology in which we do a modeling problem. Okay. Okay, let's say we've been given a task. Okay. We've been asked, okay, model something using a partial differential equation. What we first do is we'll derive or produce a PDE that describes a real world phenomena. So, for example, let's say we're modeling water. Okay, we want to have a PDE that describes the flow of water. Generally speaking, we apply assumptions to that to simplify things. So if we're dealing with water, we can assume that it's going to have constant density. That's not always the case, especially with seawater, but pure distilled water has constant density. It may have thermal properties of the same. Let's say, okay, to simplify things, our water isn't going to heat up or cool down things. Okay, so we may use assumptions to actually simplify our model. Okay, models can be built upon later. So to start with, keep it simple. Okay, have you ever heard of the acronym KISS? K-I-S-S, keep it simple, stupid. That applies to this. So start off with a simple model. You can always build on it later. And in most cases, and certainly for this course, the PDEs have already been derived. My particular research area is fluid dynamics. The equations in which I use were derived 100 years ago. Okay, so they were derived 100 years ago, but they couldn't solve them until we had computers. So in most cases, they've already been derived. Okay, then next step, derive your numerical scheme. There are quite a few different numerical methods available. You'll be doing some in this course, you'll be doing some in ordinary differential equations if you do that unit as well. Choose the one best suited for the PDE which you're solving. This may depend upon the PDE, the geometry. So let's say if you've got a complicated geometry, finite differences aren't very useful. Finite volume, which you'll be doing next term with Lynn, much more useful for that. Accuracy. If you don't need it to be that accurate, there's no point in spending ages getting a really accurate solution if you don't need it that accurate. The length of time you got to do the modelling. Back in my day, when I was doing this work, my programs would take around about 24 or 48 hours to run. Nowadays, the same programs take seconds. But sometimes you don't have that time. Things like that. These are common methods. Okay, finite difference we'll be doing this term. Finite volume method you'll be doing with Lee. Some of you may be doing finite element methods in a project, perhaps. Or those of you who are doing master's courses or the MMaths course next year, you'll be looking at what we call particle-based methods as well. Okay, so you choose your method. Everything this term is going to be focused around finite difference. Now's the fun bit. You write the program. Okay, the reason we write programs is because we're lazy. I don't know about you, but I don't want to spend all my time with a calculator, typing in numbers and calculating results. Computer programs save us a hell of a lot of work. So we write a computer program to perform the calculations for us. This can be time consuming, okay, and it can be frustrating, I realise that. Okay. Quick sort of straw poll, how many of you sort of get on with MATLAB, are friends with it? Less than half, hardly any of you. Okay. You'll learn to love it. Okay. One thing I would say is MATLAB's there to save you effort. It's a lot easier telling MATLAB to do something than it is doing it yourself. It can be frustrating at times, but it's such a great feeling when it works. Sort of punch in the air type feeling. You don't believe me, do you? You wait until your coursework. Programming should be done in steps. Don't think about a massive program and start, right, I've got to write this huge big program, let's start right now. Split it up into chunks. You build upon your program. Make sure little sections of programs work before you move on to adding something else onto it. And we often reuse or build upon existing programs. There's no point in reinventing the wheel. There's no point. If you've already done something similar, copy and paste it and adapt it to your own needs. So that's your program. So you've done the program, it works, it gives you some output. How do you know if your output is correct? How do you know that your program is bug-free? Just because it gives you some, just because it runs without any of the horrible red letters on MATLAB popping up, and it gives you some output. How do you know that output is what it's intended? Okay. So bugs in the program can affect the calculations. Let's say you put a plus where it should have been a minus, that sort of thing. Okay. To verify in the program, what you do is you perform a hand calculation, which is a little calculation on a reduced domain. So instead of saying 100 points, you may do it over 5. And you check your program gives you the same answers as you get doing it by hand. If it does, you can maybe be fairly sure that your program is verified and it's correct. Okay, so that's verifying the program. Now we've got validating the model. So if you think what we've done so far, we've built a model with a PDE, we've chosen a numerical method, we've coded it up, we've checked our program works. Okay. We might be doing absolute nonsense. We might be so far off the mark it's not worth bothering with. So you've got to validate it. So if I'm writing a program which simulates a weather model, okay, I might validate it against known weather data. Okay, so give it some initial conditions, some temperature or humidity and things like that, and run it and check it against data. This is what we call validating the model. Sometimes you can do that against analytical solutions. If there's an analytical solution, what's the point in writing a program? But very, very rare. So we normally do it against experimental or real-world data. Okay. Always got to remember a mathematical model is only an approximation. Okay? You're never going to be perfect. There's always going to be there may be sort of inaccuracies with the way we're taking the temperature measurement. You know what Heisenberg's uncertainty principle is? If you try and measure something, you're changing that thing. So if I try and get an accurate measure of temperature, right, the act of measuring it means I'm changing the temperature. So there's always some real-world experimental sort of errors creep in. If your results are different, okay, why are they different? Okay, what are the deficiencies in the model? Okay, there may be a shortcoming in the model, or there may be a shortcoming in your numerical scheme. These are all questions which you should answer. Okay, so we've done all that. Let's say we've solved the model, we've got some good results. There's no point doing all that if you're not going to tell anyone about it. There's no point you researching something or you gaining knowledge of something if you just keep that knowledge to yourself. Okay, the whole point of sort of academia, the whole point of doing this thing is to let other people know what you've done. And this is presenting the model. And we usually do that in the form of a report or a paper that's submitted to a journal, or in the example, if you're doing projects or the mini projects, those reports. Okay, and the key thing is, it needs to be clear and concise what you're doing. The reader should be able to read what you've done and have a good understanding of it. Okay, clear, concise. Should not mislead the reader. This happens. Okay, even at research level, people deliberately try and mislead the reader because they don't want the reader to reproduce their results. Okay, have you ever heard of a publish or perish phenomenon? Okay. Academics' sort of livelihoods are based upon how much they can publish. So if they've got a good idea, they'll publish it. They don't want anyone else to sort of get on the bandwagon. So sometimes people deliberately mislead. It shouldn't happen. It can happen. If the method doesn't work, it doesn't mean that you've wasted your time. It may prevent somebody else from wasting their time by doing the same thing. And that, again, happens quite a bit. You try something, it doesn't work. You chat to somebody else who's also tried that. You go, oh yeah, I tried that, it didn't work. So why didn't you tell me about it? You know, that type of thing. So this is all to do with sort of writing up, presenting. And this final one, bullet point, is probably key. It gets easier with practice, which is exactly why I get you to do it with the lab report, with the lab sheets. Okay. Is there any questions about, I'm not finished quite yet, but is there any questions on what I sort of presented so far? That means you've understood everything. Sorry?
You said you can copy and paste programs.
Yes.
No.
As long as you say, oh, this program is based upon blah, 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 blah. In the program, you need to comment. Yeah. For example, as a good example, in your assignment, I'll be asking you to write the program. What I'll say in the assignment is you may use this program to base your program on. In the comments, you can say this is built upon or based upon the program by me. So yeah, that's fine. As long as you're upfront with it, as long as you say this isn't all my work, it's fine. Any other sort of questions? Okay, I'm going to just spend the 10 minutes, or final 10 minutes we've got left, is just sort of having a look at the Moodle site and just explain what we've got. Is that over the red bit? I can't see.
Yeah.
There we go. That's not coming up at all, is it? Oh, dear me. Oh, no. Stupid, stupid. No, don't want that. Give me a sec.